Hello, this is Multivariable Calculus lesson number 1, the shell method. Now actually, it's not multivariable yet. What we're first going to do is review some of the BC topics that are no longer on the BCAP exam, but they would be in a college course. So before we begin the new lesson, let's review the integral as an accumulator. For example, if we have a function drawn that's the derivative of another function, then the area of that little rectangle you see there is f prime at that particular point times the width delta x. And so the area, if we had a lot of little rectangles filling up the whole area from A to B, would be the summation of the n number of rectangles, the heights f prime times the width delta x, which morphs into the integral from A to B if we use instantaneous dx instead of delta x, where delta x goes to 0. And then we can write f prime as df dx. And so the dx's cancel, and what we're really doing is adding up all the little changes in f. Not f prime, but the little changes in f, the antiderivative of whatever is graphed. And so what we get is the sum of all the little changes, which is the total change in f of x, the antiderivative of whatever function is drawn. And so, of course, we need a starting point. We need an initial value at a in order to figure out an actual function value. What we get from the integral is not a function value, it's the total change in the function. Another application we saw was when we did volumes. We rotate this region around the x-axis, and then we have infinitely many infinitely thin circles. And so the volume is the area of the circle times the instantaneous thickness. And so again, we accumulate all the little tiny infinitely thin volumes to make the total volume. And so we think of the integral as an accumulator. Now we're going to look at a little video, and then we'll come back to some more examples. Hello, students. Our first lesson is going to be volumes by using the shell method that was skipped because it's no longer on the BC AP curriculum. But it's an important idea, and so that's what we're going to start with, things that the BC curriculum used to have but no longer does. So let's say we have a region like this. If we rotate it around the x-axis, there's no problem because we just have nice little discs. But if we rotate it around the y-axis, we have a little problem. Well, there's a hole in the middle, which we could take care of with washers, but we're going to be subtracting the same function from itself. Now, you could, with a great deal of difficulty, solve for two different functions, one with a positive square root, one with a negative square root, and do it the old way. But this way is much simpler. Plus, what if you had a fourth degree polynomial that went and made two humps, and you wanted to rotate that? Then you really couldn't do it, because you'd have two holes, and it would be just far too complicated. So this is a new way of doing volumes. So first thing we're going to do, same as we used to, is we're going to draw the faux area over here and put dots. And then you're going to imagine rotating it. Okay? Now I'm going to turn off the camera and do some things with some construction paper, and I'll be right back to show you how it works. Okay? Okay, here's my pathetic little model. Not to scale, because all those little loops should be perfectly round. Those are called cylindrical shells because they come all the way around the back of the whiteboard. And so you have all these little infinitely thin cylinders. And so the thickness is going to make the volume, and then we're going to have to figure out the area of each shell. So in other words, we're going to take it off of this side. Hold on, taking the black spots with me, sorry about that. Take all those off and hold them out straight. And what shape do you have? Oops. Well, that one fell off. What shapes are these? Huh? Oops, well, they won't stay out straight. I need you guys here to hold them. When I do this in class, I have students hold them out. So see, if you hold them out, all these little cylindrical shells, if they're infinitely thin, you can straighten them out like this, and they're rectangles. And what's the area of the rectangle? Well, it's the height, which is the function value, and then it's the the length is the circumference, because remember they come out the back of the whiteboard too. And so the area is just going to be the circumference times the function value. And the circumference is going to be the distance from wherever you revolved it, which would be the x value in this case. And so that's the radius, so it would be just 2 pi r. Okay, so now we're going to look at an example on a PowerPoint. Okay, but that gives you the general idea of what's going on. Okay. So here's a better illustration of what I was trying to show you. I hung the whiteboard upside down so that the rectangles would straighten out. So what we're doing is we're taking the infinitely thin shells that wrap around the side of a cylinder, straightening them out, making them into rectangles with equivalent area, and then when we add up all these infinitely thin rectangular solids, we're going to get the same volume as we would have gotten from the shells. Here's another picture showing how they straighten out. So here's that same graph, and this time we'll identify the function as 4x minus x squared. We draw our faux area that we get when we rotate around the y-axis, and there's a shell, a cylinder, and so we're just using the outside of that cylinder, the cylindrical shell. And in this case, the radius of the shell is x, so we're going to use that in our computation for r. And then we're going to straighten that shell out, and we get a rectangle. And the area of that rectangle is the length that comes out towards you, which is the circumference of the shell, 2 pi r, 2 pi x in this case. And the height is just the function value. And so to get little volumes, the thickness is delta x, which morphs into dx when we have it infinitely thin. And so the volume then is going to be the integral from 0 to 4. Those are the two x-intercepts. So the area, the green area, goes from 0 to 4 on the x-axis. 2 pi x times f of x, which is the area of the rectangle, and then the instantaneous change along the x-axis to accumulate all those infinitely thin rectangular solids. And so I took the 2 pi out, multiplied x through times f of x, which makes it 4x squared minus x cubed. And then you can do that integral by hand, or you can do it on your calculator. Okay, so that was a fairly simple example. Let's try a slightly harder one. Here's another region, and this time we're going to rotate it around the line x equals 3. Here's what that function is algebraically. Negative x to the fourth plus 2x squared plus 8. There's your faux region and the cylindrical shell. Now this time the radius is not x. The radius is going from the line to the graph. And so it's 3, which would be the distance all the way from the y-axis, minus the x value, which is the distance from the y-axis to the curve. So our radius this time is 3 minus x. We straighten that shell out, and notice that we always straighten it out onto the original area. And so now we have our volume equal the integral from negative 2 to 2, which are the x-intercepts. That's the region goes from negative 2 to 2. 2 pi r f of x. And in this case, we substitute 3 minus x for r, and we substitute negative x to the fourth plus 2x squared plus 8 for f, which gets really messy. So I just typed it into my calculator, leaving the pi out so that I get the exact answer. And then don't forget to put pi back at the end. So that one equals 179.2 pi. Okay, so now it's your turn. Have fun, look at your syllabus, and there'll be another lesson posted in a couple of days.